Greetings, I'm Eray Ozkural from University of Ankara. Today I'm going to talk about, diverse consequences of algorithmic probability. Algorithmic probability, AI has had a lot of applications, and I wanted to draw your attention to three areas that I think were the most interesting. So I'll talk about axiomatization of AI, plausible interpretation consequences, what kind of plausible worldview might AI be associated with, and I'll talk about the relation between infinity point and intellectual property. So, axiomatization of AI. What is AI? It's making machines do intellectual work for us. So we would like to eventually substitute programmers and scientists, including computer scientists and statisticians, etc., with computer programs. And how can we achieve that? It turns out, I think, if you read Solomonoff's work carefully, that at least three things are absolutely necessary, and I'll try to talk about these in an informal way. There are no mathematical equations whatsoever, so we can talk about them in a light-headed manner. The first condition is that the AI has in its possession a universal computer. This could be a probabilistic universal computer, or a quantum computer, any universal machine. And the first axiom, AI0 is really redundant because AI1 subsumes AI0. The first axiom is that the AI can learn any model expressed in this universal code. So which is something we've already seen. And second is, AI uses probabilistic prediction. It applies Bayes' theorem. If it doesn't, it can't predict correctly. And third is, AI applies the principle of induction. And, as we all know, Solomonoff induction is was the most widely known principle of induction so far. There can be other formalizations of induction. Wapnick 1960 and Doe 1968. It can be formulated in a number of ways, but they're essentially the same idea, Occam's razor, as we've seen. So is that physics then is trying to cram down AI to a number of axioms? Perhaps, and I don't think that's a bad thing at all because it makes the field more scientific. So we can talk about whether we subscribe to an axiom or not. And in that regard, I think it's useful. So these axioms are my interpretation of Solomonoff's work, basically. There is another subject that's not commonly discussed, not very many people are interested in it, but it's one of the three open problems that Solomonoff defined himself. Those open problems, one of them is finding a really good universal computer for AI. The second is designing really effective update algorithms that update the universal prior so experience from problems encountered so far are integrated in the universal prior. And third is designing good long training sequences that lead up to human level intelligence. So this is the second open problem. Why is it important? Because without any memory in a system, in an AI system, machine learning is completely impossible. In realistic problems, you have hundreds of bits of complexity at least, and linear search can't be used to solve these problems. You need incremental machine learning, update algorithms. or you will have to break one of the AI axioms, in which case your system is no more an AI, but a more restricted kind of system that can't learn Einstein's general relativity or things like that. So, well, for two solutions, if every common bit of information, every mutual bit of information can double the speed of learning the second solution at best. This is a very simple, trivial application of mutual information, so I don't even prove it here. It's simple, and you can read it in the paper. I put it on the archive, by the way. You can just search for the title. And so this is the fourth axiom, I think, and I claim that it's essential. AI must use incremental machine learning or it won't work in practice. In theory it might work, but in practice it won't. So, are there practical incremental machine learning systems? Yes, there are. The one I wrote, Terra Machine, for simple training sequence, it is faster than human. And there is the 2005 or 2003, 2005 Schmidt-Huber's OOPS, and he solved Towers of Hanoi problem with it, so it's quite significant. And, well, that sort of algorithm is also called adaptive linear search because it adapts to the problems at hand, right? Again, informally speaking, because the presentation is long. And because normal linear search is infeasible. So what does OOPS have? It has the fourth universal computer. It has a simple probability model, which just says instruction probabilities, and you just multiply them. And it dynamically modifies the probabilities, so it bumps instruction probabilities. There's a special instruction for that. And results are not very convincing for transfer learning. I mean, it could have been due to chance because it's a short training sequence. So what I did, I tried to improve on OOPS a little. So Giga Machine 2009 and Terra Machine 2011. I tried to use a general purpose universal computer, full scheme R5RS, and its standard library. And I use this stochastic context-free grammar-based probability model. And we have real memory with efficient update algorithms, although the update algorithms in Terra Machine are not general purpose. They're still limited, but they are very efficient and use data mining approach. And we have parallel search, and we got some very promising experimental results at just 0.5 teraflop per second parallel computer. And it's a long training sequence, so we did show that it does work. It's not due to chance. And for deterministic problems, we have terminating programs. That's, well, it doesn't make a big difference. With respect to implementation. So, another aspect, this is a hot subject in AI nowadays, cognitive architecture. There is this argument due to Minsky, actually. I think, you know, you have this really beautiful, elegant mathematical system, but will it really work? Because we know the brain is equipped with a lot of innate information. Minsky says something like there are 400-something modules in the brain, and each are very specialized, optimized machines that evolution perfected. That's a pretty good argument, and that might actually be the case with the human brain. So, and the other thing is, you actually want the AI to be at a level that it can improve itself, it can rewrite significant portions of itself, and probably maybe it will find a better linear search or better universal computer. So the AI must be able to improve itself so it can exceed our intelligence level. And this might be considered an axiom. additional axiom. AI must be arranged so that it can improve itself. This is, I think this is optional. People don't really agree on this. But for this to be true, this must hold in practice, not just on papers. In paper, it's kind of easy to show that the system can, in theory, self-improve. I think there are two very promising cognitive architectures. Alpha in Solomonoff 2002, you can find it in an ICA technical report, is a functional design. It doesn't override stuff, it just generates new functions. It's higher order, meaning that it has higher order cognitive functions. It formalizes analysis and synthesis operations that philosophers often use. And it's quite general. It can solve general engineering problems, time-limited optimization problems, and it's completely probabilistic. The basis is probabilistic. On the other hand, Schmidt-Huber's dual machine is an agent design, basically. It starts with something like OOPS or AIXI, but then it has a reflective capability, and it uses this logic to reason about itself and improve itself. It can use intuitionistic logic or some other logic. So these are, in theory, quite promising, but it will take a lot of effort to implement them. So, well, let's talk about philosophical consequences again. There is a great paper by Hutter and somebody else whose name I can't pronounce right now. They do talk about how Solomonoff induction is a very good formalization of the general notion of induction. So you can find it in the references. I think they make a convincing case that the philosophical objections to induction are easily dissolved. Solomonoff himself says that his theory was inspired by three big ideas. Carnap's inductive inference. So the whole world can be represented by a bit string. And then science itself is predicting future bits, which is a pretty good idea. And Turing's universal computer, that there is such a mechanism that can simulate any other mechanism possible. And Chomsky's generative grammars, that we have a generative mechanism that can mechanically produce all the strings in a language. So the universal induction is obviously a synthesis of the first two ideas, and the generative grammar led to Solomonoff's, again, neglected discovery of stochastic context-free grammar, which I try to use in my work. And if you think about it, in Solomonoff's work, Solomonoff induction, the same exact method is used for both math and physics problems. There is absolutely no difference. That means there is no, if this is true, there is no epistemological difference between math and physics. And Chaitin makes a similar point. He calls it quasi-empiricism, and I subscribe to his view, but I go further. I say that math is completely empirical. Because thought experiments that we use to make maths is computation. So, well, I think mathematics is computation, self-reflective, so mathematicians develop useful programs and in a precise language to communicate them. And, okay, I'm a little short on time, so I'll skip to the other slide. And a conjecture, omega, I claim, is the golden standard of mathematics. Is every meaningful mathematical fact is reducible to a computational fact, which is present in omega. That's because, as I said, every halting problem corresponds to a kind of thought experiment, and every U corresponds to a possible world. So we're just making general statements about computation, nothing mysterious. Non-reductionism, I think, is most certainly false from an AIT viewpoint. It's the view that there are no strict bridge laws, that science is not unified. Algorithmic reducibility is a better understanding of non-reductionism. It's a better understanding than non-reductionism. And AIT is compatible with evolution. We have this a priori information that evolved. We have some universal computer in our head, it evolved, and induction. But it could all evolve. There is no need for any sort of creationism. And is there any objective universal computer? Our proposal is the universe itself. It could be a visual physics, it could be a reversible universal cellular elemental, or it could be a universal quantum computer, David Deutsch. And with respect to epistemology, in analytic philosophy there is a good definition. Knowledge is justified true belief. Our proposal was, it's the mutual information between world and brain, but that's partial. It doesn't cover justified. It could be that justified means predictive information, and verification seems sufficient. You don't need to falsify anything. And I think Solomonoff induction should be viewed as the vindication of positivism, because it does realize the two main tenets of logical positivism, what Carnap foresaw, that there's a finite cognitive procedure for inductive inference, and that's exactly what AI is. And again, can there be a unified language for science? That's what the AI's memory, linguistic memory, will turn out to be. And the analytic synthetic distinction is not required. Induction can invent logic, it can revise logic, it can go from classical logic to quantum logic. That's possible. And what about evolution? Does AI say anything about evolution? Chaitin had a big idea that the evolution tries to compute bits of omega. That's hard to prove, but I think AIT agrees with the view that life is reducible to molecular biology, because molecular biology can contain information of these overlapping physical events. And there is also the supporting twist on Church-Turing thesis, Cephalloid 2002, if I'm not incorrect. Every local quantum system can be simulated by a universal quantum computer, so you can just use that machine for induction. And non-reductionism really is intelligent design. There was this argument that flagellate bacteria are too complex to evolve. That's intelligent design. So, about infinity point. Infinity point is a scientific hypothesis that AI can improve efficiency of computing at fixed energy. That's Moore's law applied to AI. And more efficient computing can accelerate AI, resulting in a positive feedback loop, and the already exponential acceleration of computing efficiency will accelerate further, resulting in infinite acceleration in finite time, which in practice cannot be done. But it could well happen that much acceleration could occur in a couple of decades. So there's a weaker economic condition. Suppose we cannot write the right program. Even then, brain simulation is a bioinformation based AI, and many very competent people are working on that.
We have to move towards the summary.
All right.
Out of time.
Okay. Today we have 6 gigaflops per watt of energy efficiency, but by 2026 latest, we will achieve human level energy efficiency of computing. And then I hypothesize that cheap intellectual work will drive personal use of brain simulations, which will be the necessary turning point for the infinity point effects to develop. And there's an argument that I'll have to skip about intellectual property in AI, but basically, IP laws, IP latency latencycy see becomes a severe bottleneck when technology advances too rapidly. There's months of waiting for some idea to be patented, etc. And scientists already suffer from this, but in the future it will be much more severe. So I suggest that we advise the lawmakers to shorten IP protection and make it more difficult to get IP protection. They shouldn't be able to patent trivial software ideas, really. Or, well, be a member of Pirate Party. And here are some references in case you're interested, and you can find the paper on archive. Thank you.
Questions? Yes?
It was very interesting. There are lots of talks, lots of things.
Lots of stuff.
Ask about. Yeah. One point, and I've got the many. You talk about the Solomonoff study is vindicating logical positivists, partly by vindicating the idea that there's a principle of induction. I'm not sure that it's true. So what Solomonoff does is you take Bayes' theorem, which we had before then, you take the washing out of the priors, which says if you've got a prior distribution which includes the truth theorem, then eventually get a convergent. We already had that before Solomonoff. What Solomonoff did was he gave us the idea of equating theories with computer programs. But he doesn't give us a way of choosing a prior over those, right? We choose a reference machine, but depending on our choice of reference machine, we can have a radically different prior. So he doesn't give us any kind of rational basis for choosing one reference machine rather than another. So, and that's the essence of Hume's problem of induction, which is the biggest of philosophical problems of induction. Solomonoff has nothing to say about the solution to Hume's problem of induction, which is the main one.
It doesn't matter in Solomonoff. That's what convergence theorem says. It doesn't matter at all. The initial reference machine does not matter in the slightest with respect to theory. It is only a practical matter.
It's a severely important practical matter because depending on your choice of reference machine, I can give you a reference machine which assigns a given string a probability close to 1, or I can give you a reference machine which gives that same string a probability of close to 0 as you like. Okay. So,
I already mentioned the solution to that. You start off with the most objective universal computer that you can find, and that happens to be the lowest, a low-level machine that doesn't have any world information in it. It's just the simplest kind of computational law that you can find, and then you'll say.
Anyone who's doing artificial intelligence work, that's a good choice. But if you're doing philosophy and you want to rationally justify that choice, you have to justify that, right? You have to say, why does that machine, which has a simple machine table, why is that machine more likely than any other machine to... If you're referring to constructions like Ratikanians, those are hypothetical and actually physically impossible constructions. They are not relevant. Carnap was a philosopher, and Carnap was dealing with the problem of induction. That problem, the logical positivist problem, has not been solved by Solomonoff. Because
you think so?
I'm sure of it, yeah.
Well, I think actually Hutter makes, in their latest paper, they make a very good case that it does solve the philosophical problem of induction. So you should read that, I think, because I basically agree with your answer. But as I said, Solomonoff himself would say, I think, that subjectivity is a desired feature of algorithmic probability. That
he certainly did say that. Yes.
Yeah, but the real answer, the real satisfactory answer is that incremental machine learning we learn in incremental fashion. We start off with not knowing much about the world, and then we develop progressively, right? So that's how we build it. It doesn't come out of the blue, and neither does evolution create an arbitrary universal computer with lots of false information into our heads. So I think you have to take that into account, how did those universal computers evolve? They evolved or were developed by computer scientists through trial and error, through crashing those universal computers against the wall, and that's how they turn out to be the way they are, and that's why they are trustable.
Perhaps we can continue in various coffee breaks, and etc. So we can move on to Eray again.
Got you.